So we were doing circuits in the last class. Let's start with another circuit. So here capacity is C1, capacity is C2, C1 is 10 microfarad, C2 is again 10 microfarad, and C3 is 5 microfarad. You are supposed to calculate the equivalent capacitance. You have to calculate the equivalent capacitance and charge and potential and everything. C equivalent and all. C equivalent, voltage across each and charge in each. C equivalent, voltage across each and charge stored in each. So for equivalent capacitance, see, C1 and C2, they are connected in parallel. C1 and C2 are connected in parallel. So how much would be C equivalent? जो है ना, C1 and C2 are in parallel. How much is C equivalent?
C1 plus C2.
Yeah, C1 plus C2. So C equivalent is, it's 10 plus 10, or let's write this as C1. So C12 is 20 microfarad. So let's make a sub-circuit. Let's replace the C1 and C2 with a single capacitor, which is C12. Let's take this C3 and connect it with a cell. Let's say voltage of the cell is 10. The EMF of the cell is 10. Now this C12 and C3 are connected in series. So equivalent capacitance would be, now we can use C12 C3 over C12 plus C3. So you can write that your C equivalent is, it's C12 which is 20 multiplied by C3 which is 5 divided by C12 plus C3 which is 20 plus 5. So here it is 100 divided by 20. So your C equivalent comes out to be 4 microfarad. This is the value of C equivalent here, which is 4 microfarad. Now, once you have C equivalent, you will need both charge stored in each capacitor as well as voltage across each capacitor. We cannot calculate charge and voltage in this circuit directly, or we would not calculate. We can calculate, but that would be very confusing. So first of all, we will try to convert given circuit into a circuit having either all capacitors in series or all capacitors in parallel. I'm repeating it again. If you have a circuit which is a mixed circuit, means which have series as well as parallel combination. So to solve this circuit, we will first try to convert this into a circuit having either all capacitors in series or all capacitors in parallel. So let's convert this in this particular circuit where C1 and C2 are in parallel and that parallel combination is in series with C3. Now we will solve this circuit. So this is series combination of two capacitors. Johanna, in this particular circuit, which quantity is constant, charge or voltage? Johanna.
Charge.
Charge. So we can first calculate the charge stored in both capacitors C12 and C3. For this, we will calculate the total charge provided by the cell. We will first calculate total charge by cell. So the total charge by cell is simply C equivalent multiplied by the EMF of the cell. So here C equivalent is 4 microfarad. We can convert this microfarad into farad by multiplying with 10 raised to minus 6 multiplied by EMF, which is 10. So it's 4 into 10 raised to the power minus 5. So this is the charge, which is 4 into 10 raised to the power minus 5. So that's the charge stored in both capacitors. This is the total charge provided by the battery. Same charge will get stored in both capacitors. So we can write Q12 is equal to Q3, which is 4 into 10 raised to the power minus 5. We can as well calculate the voltage across each capacitor. So Giovanna, how would you calculate voltage across Q, V12?
V12 Q by C12.
Very good. Q12 by C1. So Q12 is 4 into 10 raised to the power minus 5. C12 is, it's 20, right? 20 into 10 raised to the power minus 6. So it comes out to be like minus 6, it would be 40 by 20, that is 2. So out of 10 volt, 2 volt is across C12. Johanna, can you guess voltage across C3 directly? The total is 10. Out of 10, 2 volt is across C12. So what should be voltage?
So
How much?
10 minus 2, 8 volt.
So V3 is Q3. You can even calculate using this formula. So Q3 is 4 into 10 raised to the power minus 5. C3 is 5 into 10 raised to the power minus 6. That comes out to be 8. Now we are left with Q1 and Q2. We still have to calculate Q1 and Q2. We have calculated Q12 and V12, but now we will calculate Q1, Q2, V1, V2. Okay, so we have calculated Q12 as well as V12. So here C1 and C2 are in parallel. C1 and C2 are connected in parallel. And the voltage across them is V1. So we have calculated C12. Now we will break C12 into two capacitors, C1 and C2. So C1 and C2 are in parallel. Voltage across both the capacitors would be same. So I can say, and V12 is what? V12 is 2 volt. That means voltage across each of the individual capacitors is 2 volt. You can write this as V1 is equal to V2 is 2 volt. Similarly, I can further write this as Q1 charge stored in first capacitor is C1 V1. So C1 is, how much is C1? C1 is 10 into 10 raised to the power minus 6 multiplied by V1, which is 2. So Q1 is 20 into 10 raised to the power minus 6 coulomb. Similarly, you can calculate Q2. How much is Q2? That's C2V2. C2, which is 10 into 10 raised to power minus 6 into 2, that comes out to be again 20 into 10 raised to the power minus. So this is how we have calculated Q1, Q2, Q3, V1, V2 and V3. Okay, so this is parallel combination. We will do more questions on series and parallel combination of capacitors. But before going to series and parallel combination of capacitor, we will do a series and parallel combination of resistors as well. It's because resistors and capacitors have exactly same type of numericals. The numerical that you can do with capacitor is still valid for resistors. So series and parallel combination of resistors. Series and parallel combination of resistors. See, there's a very minute difference between combination of resistor and capacitor. The only difference is in capacitor we use equation Q is equal to CV, while in resistor we use Ohm's law, V equal to IR. In capacitor we calculate energy stored using half CV square Q square by C. In resistor we calculate power. Power is energy per unit time, and the relations are I square R and V square by R. Otherwise, all other rules are same even in capacitors and resistors. So let's start with series combination of resistors. It will be quick. So you have some N resistors connected in series. Resistor R1, resistor R2, resistor Rn. So you have N resistors which are connected in series with a cell of EMF E. So Fatma, which quantity will remain same in all three resistors? Current would be same or voltage would be same? We have done this yesterday.
Voltage.
No. In these type of circuits, when there is no branching, that means the current which passes through the cell will flow through each each resistor. There is no branching in this circuit. So here current is same, but voltage will divide. It's similar to that of capacitor. Even when we did capacitors in series, same charge was stored in each capacitor, but voltage across each capacitor divides. So voltage across each capacitor divides. Okay. The first task is to calculate R equal. So you can replace the whole circuit. So in series combination, current through each resistor is same, while voltage divides. And voltage divide as direct proportional of resistance. Directly proportional means resistor having maximum resistance will get maximum voltage. It would be better if you take out those pages in which we have done that series of capacitors. If you take out the page in which we have done series combination of capacitor, that would be better, because the calculations are like similar. So instead of all resistors, we use a single resistor having resistance R equivalent. The EMF of the cell is E. Current through the resistance is I. So same in the sense, Fatima, कि even in capacitor, charge through each capacitor was same. Here too, current through each resistor is same. In capacitor, voltage divides. Here too, voltage. But yes, in capacitor, voltage was inversely proportional to capacitance because the equation was Q is equal to CV. Here it is directly proportional to resistance because the governing equation is IR. but it's quite similar just because of the division of current and voltage. So let's replace this with R equivalent. We can as well calculate total current. Total current I is, it's E by R equivalent. That's the total current in the circuit, which is EMF divided by RE. Or you can write this IE is I into R equivalent. That's first equation. Here, the total EMF of the cell divides into three parts. So you can say EMF of cell divides in resistors. The EMF of cell divides in resistors. So you can say that E is V1 plus V2 up to V. You can write E as I into R equivalent. Jabena, what would be V1?
I1, no, IR1.
Very good. V2 is IR2. It's IRN. So we can just cancel this I from the whole equation. And your R equivalent comes out to be R1 plus R2 up to R. I'm calling this as nth resistor. R. So that's R equivalent. This is how we calculate R equivalent in series. So you can see that the way of addition in series in resistor match with parallel of capacitor. In parallel combination of capacitors, we have C1 plus C2 plus C3. Here in series combination resistors, we have R1 plus R2 plus R3. Then we need current through each resistor. Fatma, current through each resistor is same or it's changing?
Same.
It's same. It's I1, I2, and it's equal to total current through the circuit. Jabena, how would you calculate voltage across each resistor? Jabena,
Sir,
how would you calculate voltage across each resistor? How would you calculate V1, V2, Vn?
Q by C.
It's not capacitor. You're doing resistor. The governing equation is Ohm's law, V equal to IR.
Okay. Then P into R, so we will get V square.
It will be IR, right?
Okay, sir.
The current through this resistor is I, resistance is R1, so the voltage is IR. So Jovana, what would be V2? First.
IR2.
What would be Vn?
IRN.
IRN, very good. So after calculating current, voltage and equivalent resistance, let's move on to power. Power dissipated across each resistor. Let's move on to power. Power dissipated across each resistor. Power dissipated across each resistor. So power dissipated across resistor is P1, which is I square R1. Because current is same, power dissipated across each resistor is I square R2. See, what is power? Power is just energy by time. If I'm saying that I'm calculating power, that means I'm calculating energy. Power is energy divided by time. So what happens in a resistor? When current passes through a resistor, it gets heated up. It's very common in electrical devices. When you pass current through an electrical device, after some time it gets heated up. The cause of heat is electrical energy convert into heat energy. And that heat energy per unit time is this power. So we're basically calculating heat energy dissipated in your resistor in 1 second. That's your power, P1 and P2. So it's I square R1 and this is I square R2. That's power dissipated across each resistor. Pn, this will be I square Rn. Fatma, what should be the total power dissipated across the circuit? Fatma, total power dissipated.
P1 plus P2 plus P3
P1,
plus Pn.
P2 up to P. Or
Sir, P1 plus P2 plus
Pn. Or
plus
we derive a relation, na? I square R1. If I substitute values. Jubena, can you guess the final result? If I keep on adding and I take I square as common.
R equal to
Very good. So your power would be I square into Re. So to calculate total power, you can either add individual powers or you can simply take this as I square multiplied by the Re. So let's start with this question. You have a resistor of 5 ohm and a resistor of 10. And it would be better if you can just unmute yourself permanently if there is no background sound, because it would be good if we can just solve this numerical by complete discussions. Juvena, let's start from you. What is the value of R equivalent here?
R
Yes, R equivalent is
I by E.
not I by E. Resistance is R1 and here resistance.
R1 plus R2.
Yes, R equivalent is R1 plus R2. So that's 5 plus 10, which is 15. Not volt, 15 ohm. Okay, Fatma, how much is total voltage across the circuit?
IR.
Total voltage. It's not IR. You need not calculate IR. You can directly write your total voltage as the EMF of cell, right? Total voltage is always the EMF of your cell, which is 10 volt.
Yeah.
After total voltage, third one. Total current is total EMF divided by total resistance. We are using Ohm's law. You must have done Ohm's law in class 10. It's E by R. So it's E by R equivalent. So your E is 10, your R equivalent is 15. So the total current is 2 by 3 amp. That's the total current in this. So this is the total current. Okay, Jubena, your turn again. Now I need current through each resistor. How would you calculate current through each resistor? Yes, Jubena.
So current is same, right?
Yeah, it's same. So the value is I1,
I2 equal to I.
yes, which is 2 by 3 amp. Very good. Fatma, how would you calculate voltage across each?
IR.
V1. So what would be V1?
IR1.
I1. Very good. So how much is I?
I is 2 by 3
R1 is,
into
so that's 10 by 3. And how much is V2? Fatma,
20 by 3.
20 by 3. You did this again using IR2, right?
Yes.
Can you calculate V2 without using R2? Is there any other method to calculate V2? Can you just guess the value of V2 if you have total voltage and the voltage across R1? No.
No.
See, the total voltage is 10 volt. Out of this 10 volts, some 10 by 3 is across 5. It's dividing. This is the same. The total voltage across the circuit is provided by cell. This voltage is being divided into two parts. So if the voltage across this 5 ohm is 10 by 3 volt, so the remaining would be across this 10 ohm. So you can even calculate this V2 as total EMF minus V1. Total EMF is 10, V1 is 10 by 3, so that's 20 by 3, right? Okay, after this series combination, let's do parallel combination of capacitors, resistors. The next we will do parallel combination. Rosa, can you guess which quantity will remain same in parallel combination, current or voltage? You can take help from parallel combination of capacitors if you want. Oh, very good. And current will divide. So this is the parallel combination. Here this is R1, this is R2, this is Rn. The EMF of the voltage is battery is E. Some current comes from the battery, it travel up to this point and then divided into n parts. For first resistor it's I1, from second resistor it's I2, from nth resistor it's In. So current get divided into n parts. Voltage across each is same. Voltage across R1 is E, R2 is E, Rn is E. Same voltage across each capacitor. So I should better write this as V1 is E, V2 is E, Vn is E. So that's how we calculate voltage across each resistor. So in parallel combination, voltage across each resistor is same. While current divide. Across each resistor, voltage is exactly same, but current will divide. So we can replace all these resistors with a single resistor. Say the resistance is R equivalent, EMF is E, so the current is R. So total current through the circuit can be written as it's E by R equal. That's total current through the circuit. Total current through the circuit I is E by R equal. So this is the total current through the circuit, which is E by R. Now this current I gets divided into n parts. So you can write this as current divides. So your total current I is I1, I2 up to IN. So it will be E by R1. I2 will be E by R2. And IN is E by R. This E gets cancelled out. And you can simply write 1 by R equivalent is 1 by R1 plus 1 by R2 up to 1 by R. So this parallel combination of resistor exactly match with this of series of capacitors. So if you have two resistors, for two resistors, Jubena, what should be the final result for two resistors? If we have two resistors, what should be R equivalent? Can you
R1 plus R2.
R1, R2
R1 plus R2.
by R1. This we can use for two if you have only two resistors. Next, Afroza. So, what is the voltage across each resistor? Yes, it would be. Can I directly write that voltage across each resistor is E? Since all are connected in parallel, so voltage across each resistor is equal to the EMF. The next is current through each. So how much is I1, Afroza? E by R, right? See, we are using Ohm's law. Ohm's law that you must have done in class 10, that current is voltage by resistance. So we can write this as that your I1 should be V1 by R1. V1 is E, so it's E by R1. Similarly, you can write I2. It's V2 by R2, which is E by R2. Similarly, IN is E by R. So these are some relations that we will use in numerical. Just note it down. So for power, we will use formula power dissipated across each resistor. So power dissipated across each resistor would be V square by R. So we will use V1 square by R1. V1 is equal to E, so you can simply write this as E square by R1. Power dissipated across second is V2 square by R2, which is E square by R2. And we can even write Pn, which is Vn square by Rn, which is E square by R. This is how we calculate power dissipated across each resistor. V square by R1, V square by R2, V square by R. And for total power, for total power dissipated, you can write your P as P1 plus P2 up to Pn. Or you can write E square by R1 plus E square by R2 up to E square by R. So you can write this as E square is common. You are left with 1 by R1 plus 1 by R2 up to 1 by R. You can write this as E square by R equal. So you can write this as P is E square by R equal. Next question. So we have two resistors, a resistor of 5 ohm and a resistor of 10 ohm. They are connected to a battery of 10. Afroza, what is R equivalent? How would you calculate R equivalent here? Yes.
R1 plus R2.
No, not R1 plus R2. It's parallel. R1, R2 by R1 plus R2. So it would be 5 into 10 by 5 plus 10. So that's 50 by 15, which is 10 by 3. Okay. Next, I need total voltage across the circuit. So, Afroza, what is total voltage?
10.
Yes, it's total EMF of the voltage, right? It's 10. Now, can you guess total current in the circuit? Afroza. How do you calculate total current?
E by R equivalent.
Yeah, it's total EMF by R equivalent. So total EMF is 10. Your R equivalent is 10 by 3. So your total current comes out to be 3 ampere. Very good. Fourth, I need voltage across each capacitor. How would you calculate that?
IR.
No. You can calculate that directly. Fatma, how would you calculate voltage drop across each resistor directly without using current?
It's EMF 10 volt.
Both are equal to EMF, which is 10.
Q by C.
Not Q. Q is for capacitor only, na? These are resistors. That C is not valid for resistors. There's no capacitance. These two are connected in parallel. In parallel combination, voltage across each resistor is same. So you can just write this as V1 is equal to V2 equal to E, which is 10. Fifth one, I need current through each resistor. Yes, Afroz, how would you calculate current through each resistor?
E by R1.
Yes, it's V1 by R1. And how much is V1? It's equal to E,
10.
which is 10 by 5, which is 2 ampere. Afroza, what is I2? How would you calculate I2, Afroza?
V2 by R2.
And how much is V2?
V2 is 10.
What about R2?
R2 is 10.
R2 is 10. So it's 1 ampere. Very good. Next, I need power dissipated across each. Power dissipated across each resistor. Just
For P1 E square by R1.
V1 square by R1. So how much is V1? V1 is 10. 10 square by 5. It's 100 by 5, which is 20. The unit of power is what? Afroza, how would you calculate P2?
V2 by R2.
V2 square
V2 square by R2.
would be 10 square by 10. It comes out to be 10. And how would you calculate the total power?
Vn by Rn.
We can use V square by R equivalent, or we can simply just add individual powers. Now, instead of only series or only parallel combination, we'll take a numerical having mixture of series and parallel. Let's take this numerical. We have solved similar numerical with capacitor. So that's 10 ohm, that's 10 ohm, that's 5 ohm. It's R1, it's R2, it's R3. And say here this is 10 volt. The first part is we have to calculate Re equivalent. So see, it's a mixed circuit. Here R1 and R2 are connected in series. With a series combination in R1 and R2, this R3 is in parallel. To solve this circuit, we have to make sub-circuits. We first have to pick the series combination. Let's take a resistor R12, which is series combination of R1 and R2. R1 and R2 are connected in series. So we can take R12, which is series combination, and R1 and R2. So you can simply write that your R12 is 10 plus 10, which is 20. Now, next make a sub-circuit. Instead of R1 and R2, use a single resistor. Sorry, not capacitor. So just remove this R1 and R2, and instead of R1 and R2, use a single resistor R12. Along with R1 and R2, take another resistor R3 in parallel, and this is your cell of 10. So Jumena, what type of combination is this?
Parallel.
Parallel. So what would be the R equivalent in this case? 20 and this 5?
R1, R 20 into 5 by 20 plus 5. So 100 by
Yes.
25.
100 by 25. So that would be only 4, right?
Yes.
So this is R equivalent. So next, we need total voltage across the circuit. Afroza, can you guess what is the total voltage across the circuit?
10 volt.
It's always the EMF of the cell. Very good. It's 10 volt. Okay, Jubena, if I ask you to calculate total current, how would you calculate total current in the circuit?
Total current
Yes,
E by R equivalent
it's always E by R equivalent. So how much is E?
10.
10. What about R equivalent? 4.
4.
So that's 2.5 ampere. Very good. So after this total current, the next is voltage. No, we can't solve. We have to calculate individual current and voltage. Now we can't calculate individual current and voltage through this circuit only, because this have combination both series as well as parallel. I'm repeating it again. To calculate individual current and voltages, you need a simplified circuit, a circuit having either all resistors in series or all resistors in parallel. We can't use this circuit. We can use, but we will not use because it's very complicated. First, we will solve this circuit. After solving this circuit, we will come to this circuit. So for individual and current and voltage, I'm solving this circuit. This is R12, this is R3, this is 20 ohm, this is 5 ohm, and you have a cell of 10. So Froza, can you guess voltage across R12 and R3 in this circuit?
They are equal.
Yeah, equal to what?
Equal to E.
Equal to E. Very good. That's equal to 10. Now, once you have voltage, Fatma, can you guess how do you calculate I12 current through this R12?
E by R12.
V12 by R12. So that's 10 by R12. R12, how much is R12? That's 20. It comes out to be half ampere. What would be I3? Fatma?
V by R3.
How much is V3?
10. 10.
10. And what is R3? 5.
5.
Comes out to be 2. Okay. This R12 still need to be solved. To solve this R12, we can just expand this R12. What was R12? R12 was series combination of 10 and 10. So just expand this R12. This is R1, this is R2. This is R1, this is R2. That's 10 ohm, that's 10. That's V12 voltage. And current through them is I1. So Juvena, which quantity is same in R1 and R2? Voltage or current?
Current is same.
Current is same. How much is I12? I12 is half ampere. So you can say that I1 and I2 current through each resistor is equal to the I12 current, which is half ampere. Now, if you have I1 and I2, Afroza, can you tell me how would you calculate V1, voltage across first resistor, V1?
I1 is equals to V1 by R1.
So V1 is I1 R1. We have already I1. We have to calculate V1. So it's half into R1. R1 is 10. That comes out to be 5 ohm. Similarly, you can calculate V2, which is I2R2. So that's half into 10. It comes out to be 5. What is current through this 10 ohm resistor? How much is current? It's half ampere. What is voltage across this resistor? It's 5 volt. The current through this 10 ohm resistor, 0.5 ampere. How much is voltage? 5 volt. Current through this 5 ohm resistor is I3. Where is I3? I3 is, how much is I3? It's 2 ampere. Voltage across this is 10. So this is how we solve the entire circuit. First, divide that circuit into a circuit having resistors and series, and either all resistors are in series or all are in parallel. First one. See, R1 and R2 are in parallel, right? So you can see R12 is R1 R2 over R1 plus R2. So that's into 10 into 10 by 10 plus 10, 100 by 20, which is 5. So that's R1. So you can combine R1 and R2 as R12, which is 5 ohm, R3, which is 5 ohm. This is cell of 10. No, not 5 by 2. Okay, just check your steps now. So your R equivalent is no, it's 10 ohm. Check your calculations. Okay, tell me if you have any doubt in this second part. Now we need total current and total voltage. So for total current and total voltage, we will start from this circuit. I don't exactly need total current and total voltage. I need current through each resistor and voltage through each resistor. For this, we can start with total current. Total current is total EMF by equivalent resistance. Total EMF is 10, equivalent resistance is 10, so current comes out to be 1 amp. So this 1 ampere is current is flowing through. So both I12 and I3 will be equal to 1 amp. Next, if you have I12, you can, okay, you can calculate V12. V12 is I12 into R12. So I12 is 1, R12 is 5. So your V12 is 5 volt. Similarly, you can calculate V3. V3 is I3, R3. I3 is 1, R3 is 5, so your V3 is 5. V3 is 5. Now, after V12 and V3, the next is, now we have to solve this R12. What is R12? It's parallel combination of R1 and R2. So Fatma, in parallel combination of R1 and R2, which quantity would be same? Current or voltage?
Voltage.
Voltage. And what's that voltage? The voltage which is across R12. What is voltage across R12? That's for 5 volt. That is the total voltage. So you can write that V1 is V2 which is V12, which is equal to 5 volt. Is it clear? So Fatma, how would you calculate I1 now? If you have V1, how would you calculate I1 now?
V by R1.
So what is V1 and what is R1?
5 by 5. 1.
What is R1? R1.
10.
So how much is? It's half amp. And what about I2?
Same. 5 by 10.
Let's do one numerical of NCRT, then we will do something else. So you have some capacitors. C1, C2, C3 and C4. You're supposed to calculate the equivalent capacitance. So see, in this is the battery. This is the battery. Now, see some rules to decide series and parallel combination in a complicated circuit. For series, always look for capacitors without branching. These two capacitors are in series. There should not be any branching, no branching for series combination. Because you will not get straightforward circuit. The circuit that you will get will need time to analyze. So series combination, no branching. This is series combination. This is C1 and C2. This is again series combination. There is no branching. So we look for these types of terms in the circuit. So the terms having no branching are connected in series. For parallel, we look for end-to-end connection. We will look for end-to-end connection. Means if you have two capacitors, they should be connected end-to-end. The same rules are for resistors. If you have resistors like this, they are in series. If you have resistors like this, they are in series. For parallel, there should be end-to-end connection. One plate of one capacitor should be connected to another. One plate of one capacitor should be connected to another. Resistors should be connected end-to-end. One end of resistor is connected to second end. These two are in parallel. But remember, if you have capacitors or resistors in this way, there is a branching, no series. They are neither in parallel. It's not necessary if capacitors or resistors are not in series, then they must be in parallel combination. In majority of cases, capacitors are neither in series nor in parallel. Not all capacitors are always connected in series and parallel. In this example, no series because due to this branching. Similarly, Fatma, tell me, are these two capacitors in parallel?
Yes.
Okay. If I put one capacitor here, are these two in parallel now?
No.
No, because for parallel combination, you need end-to-end connection. One end of this capacitor should be connected to this end. So, no parallel combination. So, make a note in your notebook and write these terms. These terms will help you in complicated circuits. Now, just look at this diagram and tell me, are C2 and C3 are connected somehow? Are they connected in series or in parallel, this C2 and C3? This is your cell. This 300 volt is your cell. I'm
Right.
again, it's not necessary that all capacitors are either in series or in parallel. It may be possible that they are neither connected in series nor in parallel. So can you guess about this C2 and C3? Are they connected in series or in parallel or no combination? Series, right? Afroza, if you look at this C2 and C3, Is there any branching in between C2 and C3, Afroza? This is C2 and this is C3, Afroza. There is no branching. Then, yeah, they are in series. C2 and C3 in series. Very good. For series combination, I can write C23. C23 is C2 into C3 by C2 plus C3. So this C2 is 200 into 200, 200 plus 200 would be 100. So this is C23, which is 100 picofarad. So that's C23, which is equal to 100 picofarad. So now let's make a sub-circuit. We have C1. Instead of C2 and C3, I put one C23. And then I've taken this C4. And this is the battery. This is okay, now tell me, are these two capacitors connected in any type of combination? C1 and C23. Jovana, if you look at C1 and C23, this is C1, this is C23. They are connected end to end. They won't be in parallel if you have something in between C1 and C23. See in this whole diagram, this one. C1 and C23 are connected end to end. There is nothing in between. So C1 and C23 are in parallel. One more thing. Can I consider all these three in parallel? Yes or no? Can I consider all these three in parallel? Afroza says no. Okay? No. Giovanna, all three. C1, C2, 3 and C4. No. We can't consider them in parallel. The reason is because C2, 3 and C4 are not connected end to end. Yeah, there is battery in between, very right. So C2, 3 and C4 are not connected in parallel. So only C1 and C2, 3 are in parallel. So we can take their parallel combination and name this as C123. So that's C1 plus C23. So your C123 is C1, which is 100. C23, which is 100. C123, which is 200 picofarad. This is C123. Okay, so we have combined all these capacitors. So using this C1 and C23, I can write C123. So we are left with, this is C123 and this is C4. And this is cell. Okay, now tell me C123 and C4, series, parallel or no combination? C123 and C4. Okay, what about you, Jovana? Now this time we all are wrong. See, if I move from C123 to C4, is there any branching? If I move from C123 to C4, is there any branching? Like if I'm moving from here to here, there's no branching. If there is no branching, that means these two capacitors are in series. Whether I draw it like this or I draw it like this way, that is the same way, the same thing. Just by changing the position of a cell or battery, equivalent capacitance does not change. So it's C4 into C123 by C4 plus C123. So C4, it's 100. C123, it's 200. C4 it's 100. C123 it's 200. It's 100 into 200 by 300. So it's 200 by 3 picofarad. That's the final answer. There's one more question. How these resistors are connected? Series, parallel, or no combination? 3 resistors. How they are connected? Series, parallel, or no combination? Series, huh? So the answer would be R plus R plus R3R. How are they connected now? How are they connected now? They are not in series. So for these types of circuit, the method of geometry that I have just taught, that by looking at the branching, you can decide whether your capacitors are series or in parallel. That method will not work in these type of circuits. These types of circuit cannot be solved by using just geometry. For these circuits, you need some methods. So this circuit can be solved using potential divider method. Using just potential divider method. So this is point A. If this is point A, that means potential over this point is A, V. If this is VA, see, each and every point which is connected by a straight wire, a conducting wire, is at same potential. If I say this is VA, can I say this is VA? Yes or no? If this is VA, can I say this is VA? No, because due to this resistance, your potential will change. But if this is VA, can I say this is VA? If this is VA, can I say this is VA? Yes. Yes, we can say this is VA. This is VA. Yes, we can say this is VA. This is VA. Connected by the same wire. Let's call this point as VB. If this is VB, then I can call this as VB. So this is my resistor number 1. This is my resistor number 2. And this is my resistor number 3. Say potential difference across R is VA minus VB. This is the potential difference across R. Potential difference are 1, 2. What is potential difference across R2? It's VB, and at another end, this is VB minus VA. Similarly, potential difference across R3 is again VA minus VB. Is this step clear to everyone? That potential difference across each resistor is VA minus VB, right? Great. So see, when we are checking series and parallel combination, then VA minus VB and VB minus VA are the same thing for us. I'm repeating it again. When you are just checking series and parallel combination, you can take this VA minus VB and VB minus VA as the same potential difference. So can I say that potential difference across R1, R2, and R3 are equal? Can I say that potential difference across R1 and R2 and R3 are equal? If potential differences are equal, then what type of combination is this? Is it series or is it parallel combination? If you have forgot, just turn your pages.
Parallel.
This is parallel, very good. If your capacitors are, if potential difference is same, that means your combination is parallel. All these capacitors are connected in parallel. Resistors are connected in parallel. So it's actually this combination. We just have flipped some wires and it's looking complicated. Here the points A, B simply means that you can attach a virtual battery through these points. Say, calculate potential difference across A and B. So you can say that fictitious batteries are attached across A and B. That's R and R. So you can very well write this as 1 by R equivalent is 1 by R plus 1 by R plus 1 by R. So you can write your R equivalent is 3 by R. You can write your R equivalent is R by 3 now. That's R equivalent. Clear? Let's solve just one more numerical. Calculate R equivalent. I won't solve this circuit. Solve this circuit, get the value of R equivalent. This is 1, this is 2, this is 3. It's a very simple circuit. All these three are not in series. See, check it. See. From here to here, there is no branching. But if I move from R to this R, there is branching, na? In these two resistors, there is no branching. In these two, there is no branching in these two resistors. But if I try to include this one too, then there is branching over this point. So this 3 is not in series with 1 and 2. Clear? Three is not in series with 1 and 2. Okay, let's solve and check your answers. 1 and 2 in series. So R12 is R plus R, which is 2R. So instead of this 1 and 2, let's substitute a single resistor. Let's make a sub-circuit. If you are not making sub-circuits, then you can make mistakes. If you are not making sub-circuits, there are chances that your answer would be wrong. Make sub-circuits. Now you can guess that 2R and R, how are they connected now? Series, parallel, and or nothing? Yes, Afroza is correct. Jubaina and Fatma, how are they connected now? Yes, they are connected in parallel. Right, they are connected in parallel. So your R equivalent will be R12, R3 by R12 plus R3. So it's 2R into R. 2R square by 3R, it's 2R.